Okay, good morning everyone. So today we have Nathan Kaib, who is assistant professor at the University of Oklahoma. So Nathan got his PhD in 2010 from University of Washington. Then he was actually CITA fellow, National CITA fellow at Queens. He's expert on everything dynamics, solar system, exoplanets, collisions, and whatnot. Today he's going to tell us about the late instability and outer solar system. Nathan?
Okay, thanks for the introduction. So actually I'm going to tell you that the late instability wasn't all that late. Yeah, so I realize this title's a little abbreviated. It should say the giant planet instability in the outer solar system. So this is work I've done with several collaborators, my graduate student Matt Clement, postdoc Billy Quarles, and then John Chambers and Scott Shepard at Carnegie Institute, Department of Terrestrial Magnetism in DC. And this work's being funded by the National Science Foundation. And so I'll just start with this diagram of the solar system. So you probably all have seen one of these before. So when I first learned about the solar system, my general impression was, when we see the orbits of the giant planets, that kind of marks where they formed. And they basically, the planets formed, and then they've been in that position for a very long time since then. But starting in the 1980s, our ideas about what's happened to the planet since they formed has changed quite a bit. And one of the first major changes in that understanding came with this paper by Fernandez and Ip in 1984. And so what they realized is if you just laid down a bunch of small bodies among the giant planets, the giant planets would migrate. And they wouldn't all migrate in the same way. So in this paper, there's this classic plot which shows the semi-major axis evolution of Neptune, Uranus, and Saturn, and Jupiter over time as they interact with planetesimals. And basically what this boils down to is that Neptune, Uranus, and Saturn aren't as efficient at ejecting things as Jupiter is. And as a result, to conserve angular momentum, Neptune, Uranus, and Saturn move out over time as they interact with planetesimals, and Jupiter moves inwards. And so when this was first published, it wasn't clear if this actually occurred in our solar system, but if there was a large population of planetesimals in the in the outer solar system, you would expect the planets to behave this way in response. Another piece of the puzzle came with this publication by Renu Malhotra in 1993, where she looked at the orbit of Pluto. So, when the good old days when Pluto was still a planet, its orbit seemed, compared to the other planets, was pretty unusual. It had a relatively high inclination, relatively high eccentricity. And one thing she noticed, or one thing she discovered, is you could actually reproduce Pluto's orbit starting from a circular orbit if you allowed Neptune to migrate by about 5 AU. So to start, basically she just integrated Pluto and Neptune, well, Pluto on a circular orbit, and started Neptune at 25 AU and slowly moved Neptune out to about 30 AU. And right here, you can see what's plotted right here is basically it's the mean motion of Neptune divided by the mean motion of Pluto. But you could also think of this as their orbital period. And you can see that very quickly, this object that's supposed to represent Pluto gets caught in the 3-to-2 mean motion resonance with Neptune. So while it's in the 3-to-2 mean motion resonance, Neptune's continuing to migrate. And if you place an object if you are trapped into a mean motion resonance with a migrating planet, over time what can happen is your eccentricity can be pumped up. And in this particular plot, or in this particular example, the eccentricity starts off at 0 and is pumped up to a value fairly close to Pluto's in the course of this is over the course of a few million years. And so this was a natural explanation for how you can get the orbit of Pluto starting out from a circular orbit just beyond Neptune. And a follow-up work in 1995, so we didn't discover the first non-Pluto Kuiper Belt objects until the early 90s, but a follow-up work in 1995 by Renu Malhotra showed that if there is a large Kuiper Belt beyond Neptune and Neptune migrates some, what you'd expect is that not only will you generate orbits like Pluto, but a large portion of all the Kuiper Belt objects that are out there should be trapped in these mean motion resonances with Neptune. And so what you have right here is the result of 2 different simulations she ran, where basically Neptune was started at 25 AU and was allowed to move out to 30 AU. And these distributions right here, marking particle eccentricity versus semi-major axis. These are 2 separate simulations. These are the initial conditions. So just starting with very low eccentricities, and then she just allowed Neptune to migrate out. And these are the final distributions right here. And you can see that a lot of the material, if it doesn't get ejected, it winds up trapped in mean motion resonances. And here's a plot just showing the inclinations instead of the eccentricities. And you can see, again, they're aligned with mostly the 3-to-2 mean motion resonance and the 2-to-1, but there's also some in the 4-to-3 and 5-to-3 as well. And so when this plot was made, we knew of just a handful of Kuiper Belt objects. But since then, we've discovered roughly 1,000, over 1,000 objects orbiting beyond Neptune. And these are the results of detections from the Outer Solar System's Origin Survey, a paper by Michelle Bannister last year, showing the detections in this survey. This survey detected roughly, by the end of it, this is the first quarter detections. By the end of it, it detected almost 1,000 Kuiper Belt objects. And you can see that, again, if we look at eccentricity and inclination versus semi-major axis, these 2 plots don't look all that different. You can see there's a big pile up in the 3-to-2 resonance, more in the 2-to-1. So of course there's observational bias that's built into here, so you're much less likely to detect stuff out here compared to in here. But you can see that there's clear concentrations of material at the resonances with Neptune. And so again, this successfully predicts, so if we had migration, the prediction is that there should be an abundant number of Kuiper Belt objects in resonance with Neptune. And this is actually what we see. And so just to illustrate what goes on here, this is just a simulation I ran for a paper with Scott Shepard where we constrained basically the migration rate of Neptune, where basically we have Jupiter, Saturn, Uranus, and Neptune. And just beyond Neptune, we have a disk of test particles that runs from about 25 AU out to 30 AU. And here's their inclinations, and here's their eccentricities. And this dashed green line right here basically marks material that has a paracenter either above or below 32 AU. So stuff up here has a paracenter that's lower than 32 AU, which means it's basically directly scattering off the planet still. Stuff out here has a paracenter a little bit further away. But we can start this simulation. You can see Neptune migrates out. In this particular simulation, it migrates out over the course of about 300 million years and then stops. And then the simulation continues for a total of 4 billion years. And you can see over time, the Kuiper Belt is just eroded more and more. And you get this nice resonant structure that I just talked about before. And in addition, you still have a large body of, or a large population of objects that's not in resonance, but there's the resonances are clearly a significant part of the population. In addition to that, there's other evidence that the Kuiper Belt was formed through this migration, or through basically giant planet evolution. So if you look at the physical properties of Kuiper Belt objects, what we see is that they can basically be divided up into two different groups. There's groups with there's objects with low orbital inclinations, and they tend to have one color. And there's groups with there's another group with high orbital inclinations. They tend to have another color. They tend to be bluer in color. So, although this is a good paper, I don't like this plot because it actually the colors are exactly the opposite of what we actually see in the Kuiper Belt. So again, low inclination tends to have a red color. High inclination tends to be a slightly bluer color. And just so you know, so this is inclination versus semi-major axis, and this runs from the 3-to-2 resonance with Neptune out to the 2-to-1. And so this paper by Rodney Gomez in 2003, basically he showed that what this is telling us is that since these things have different physical properties than these things, one assumption could be that they formed at a different distance from the sun. And if you allow your Kuiper Belt to be formed by a Neptune that migrates through a disk of material, what you find is that the low inclination guys preferentially come from the outer part of the disk, And the high inclination objects that are a different color preferentially come from the inner part of the disk. So you could imagine, this when the sun first formed, when the solar system first formed, the material over here formed at a different temperature, had a somewhat different composition than the material over here, and that leads today to a Kuiper belt where you have high inclination objects have one color and a different composition, and low inclination objects that have a different color and a different composition. So another important development in the thinking about how the giant planets could have evolved over time is that up until this paper in 1999 by Ed Thomas, Martin Duncan, and Hal Levison, it was presumed that whatever migration took place had to be smooth in nature. It had to, there weren't any violent changes in the orbital elements of the giant planets. But what they did is they basically took the same initial conditions as the Renu Malhotra work. Basically, you have the giant planet surrounded by this massive disk. And instead of putting Uranus and Neptune right beyond Jupiter and Saturn and allowing Neptune to migrate, what they did, you can't really see it here, but what they did is they took Jupiter and Saturn, and then they put the two ice giants, Uranus and Neptune, between Jupiter and Saturn, and just evolved the system and let it go unstable. So that's not a stable configuration. You can see what's being plotted right here is the lower line of each color is the perihelion, the upper line is the aphelion, and the center line is the semi-major axis of each body. And so what happens is Uranus and Neptune get scattered by Jupiter and Saturn to larger semi-major axis orbits. And you can see that their eccentricities are quite high. However, once they get scattered out into the 20 to 30 AU range, you have this massive disk of planetesimals out there. And what happens as Uranus and Neptune interact with that massive disk of planetesimals, they experience dynamical friction, and this recircularizes their orbits on a more widely spaced set of orbits. And so in this paper, they ran several simulations of this process, and they were able to reproduce the space. This is one of the best results here, that they were able to generally reproduce the spacing of the planets that we see today, and they also produced a Kuiper belt that is just generally stirred up, dynamically stirred up like the one we see today. Now, in their simulations, they let the Kuiper belt run out to 60 AU. We don't believe that that actually happened now. It seems the circular orbits in the Kuiper belt seem to peter out right around 47, 48 AU.
So part of the reason for starting stepping closer in was to make it easier to form them?
Yes. So that's another issue is the formation timescales. The accretion of their cores, of their ice cores, takes much longer at 20 to 30 AU versus, let's say, at 8 AU or something like that.
Did they have other motivations besides, hey, let's try it? Or?
No, I think their motivation was these planets could form much more quickly if we put them at, inside 10 AU versus.
And Saturn, the green lines, right? Is that circularizing because of it's also interacting with planetesimals?
Yeah. So what happens when you throw a couple ice giants into the planetesimal belt? Typically, what happens is they get scattered inward, and so they wind up interacting with Jupiter and Saturn as well before Jupiter ultimately ejects them.
I see.
Yeah. Mm-hmm. And so the bottom line is that you could yield something somewhat similar to our solar system with a violent evolution of the giant planets instead of just this smooth migration that I was talking about before. And so this kind of spurred a new idea. Or before I get there, let me talk about one consequence of Neptune's migration. So you actually hit on this. So when Neptune migrates, or when Neptune enters this primordial disk of planetesimals, most of those planetesimals that Neptune interacts with, they aren't directly ejected by Neptune. Instead, Neptune scatters them inward, where they interact with Uranus, and they get scattered inward again by Uranus, where they interact with Saturn. And then it's Jupiter that ultimately does the ejection. And so due to this process, as I said before, Saturn, Uranus, and Neptune move outward over time, and Jupiter moves inward, and that's just due to conservation of angular momentum as they interact with the planetesimals. And so so the fact that Neptune has migrated means that Saturn has also migrated outwards over time too. And what that also means is that Jupiter and Saturn's orbits have diverged because you have Saturn moving out and Jupiter moving in. So if you look at the period ratio of, actually this should be the period ratio of Saturn divided by period of Jupiter. But anyways, imagine that J and S are switched. But anyhow, today that period ratio is just under 2.5, so it's 2.48. And what that means is that in the past, as the giant planets were more compact, that period ratio had to be a smaller value than it is today. And at some point, as you go back in the past, if the amount of planetesimals that was ejected was tens of Earth masses, this implies that the original period ratio was below 2. And that's important because to get to the current value, at some point this value had to cross 2. And briefly, Saturn and Jupiter were in their 2-to-1 mean motion resonance. And so if you have the two most massive planets in a 2-to-1 mean motion resonance, that produces a strong perturbation, a very strong perturbation on the rest of the outer solar system. And so this led to what's known as the Nice model, where basically the outer solar system is destabilized during this resonance crossing. So this is a movie you may have seen before of this type of instability. So we have Jupiter shown in the red orbit, Saturn with the yellow, and then this dashed yellow line, which you may or may not be able to see, is just beyond Saturn's initial orbit. That marks the 2-to-1 resonance with Jupiter. And then we have Uranus and Neptune surrounded by a large disk. So we'll evolve this over time, and nothing much happens for about the first 800 million years, but there is a very slow march, you really can't see it in this diagram, where the actual orbit of Saturn is getting closer and closer to that 2-to-1 mean motion resonance. And so we have a couple 100 million years to go here. But basically, when these two planets hit their 2-to-1 mean motion resonance, that greatly excites the eccentricities of Uranus and Neptune. So here it slows down when this happens. So Uranus and Neptune have their eccentricities greatly excited. They wind up strongly scattering off of each other. They can even scatter off of Jupiter and Saturn. And they get tossed out, just like in that Thomas et al. 1999 paper. They get tossed right into the middle of the primordial Kuiper belt. Dynamical friction takes over, and we recircularize the orbits onto a more widely spaced set that we see today. And this would imply that what we see in the Kuiper belt today is just the little bit of material that's left over from that massive primordial disk. And so one of the reasons that this idea called the Nice model was seized so enthusiastically to explain the early evolution of the solar system is simply because, let me go back here, simply because if you remember in this movie, all the action didn't happen right away. So because of the way the planets were arranged, there was a large gap between the outermost planet and the primordial Kuiper belt, and Jupiter and Saturn were significantly closer than their 2-to-1 mean motion resonance initially. So what that led to is that there wasn't an instability that occurred until about 800 million years in. So you can have this resonance crossing feature that causes the destabilization of the outer solar system that can be kind of tuned to produce an instability on whatever time scale you want. And so this was connected with the cratering record on the moon. So through the Apollo missions, the rocks returned in the Apollo missions, we attempted to date a lot of these major impact basins on the moon. And so although there's a lot of uncertainty in this, there's at least a camp of geologists that believe that a lot of the major impact basins, including Embrium and Nectaris, all date to within about 100 million years of each other. Here's another plot, a histogram showing basically the distribution of impact melt events gathered from lunar rocks. And you can see that there appears to be this big spike at about 4 billion years in, whereas the Earth and Moon system formed about 400 to 500 million years before this occurred. So based on these findings, it's been proposed that the impactor flux on the moon may have followed an evolution like this, where basically you form the terrestrial planets and you form the moon, and initially you have a high flux of impactors, and you clear out the inner part of the solar system, and then it dies off. And then to form those younger impact basins on the moon, you have a second spike in the cratering record on the moon. This is known as the lunar cataclysm. And so that's a fairly controversial idea, but it's been around for a long time. And the Nice model, this resonance crossing between Jupiter and Saturn, could naturally explain how you could have this dramatic spike in the number of impactors about 500 million years after the planets have formed. So there's alternative explanations for this. You could just be basically looking back to a saturation point on the moon, where you have a smoothly declining population of impactors, but basically before 4 billion years ago, the impact rate's so high that you're constantly just resetting the ages on the moon, and so you just never see anything older than about 4 billion years. And there's also alternative impactor flux evolutions as well. Yes, but I would say that in the last 10 years, so I'm no geologist, but I would say that in the last 10 years, my impression among geology literature is that there's a growing amount of skepticism with this idea of a late spike.
So it's because of the dating itself, right?
What's that?
So the skepticism is because of the dating itself.
Yes, yes, yeah.
If you saturate the surface, you melt the entire surface.
Yeah.
The impacts reset the clock.
There's also an idea that a lot of the rocks we picked up, even at other parts of the moon, were just contaminants from the Imbrium basin too. So we could just be dating one basin. So in addition to that, that's one issue, and then the name escapes me at the moment, but there's another impact basin where reanalysis has shown that particular impact basin occurred about 4.2 billion years ago, whereas Imbrium is pretty well dated to about 3.8, 3.9. So all of a sudden, this spike has gotten a little bit more drawn out in time, and so those two things combined, I think, has led to a good deal of skepticism that the second spike is actually real. Yeah?
Do you have a sense of how many data points we have? 10, 100, 1,000, 1 million?
Less than 1 million. Yeah.
So the errors on those measurements are like pretty large.
Yeah. Mm-hmm. So, but I'll continue with the story about the Nice model initially. So, here's another plot of this. So basically showing, again, just like before, this is just the perihelion and aphelion of the giant planets, and then they hit their resonance. Jupiter and Saturn hit their resonance crossing at about 800 million years in. And if you look at the predicted number of small bodies that would be passing through the inner solar system and potentially hitting the Earth, if you look at the comets which will be coming from that massive primordial Kuiper belt, there's this huge jump in the potential number of impacting bodies at 800 million years in when you have this resonance crossing. And then in addition to that, follow-up work basically modeled a asteroid belt during this resonance crossing, and basically the asteroid belt is heavily depleted as well. So you get large populations of impactors from both the asteroid belt and the Kuiper belt during this event. So one consequence of this is if you want to have a delayed instability to explain a late spike in the cratering flux on the moon, that obviously means that the terrestrial planets are fully formed when the giant planets go unstable. And so these initial papers didn't investigate the stability of the terrestrial planets at all. And one reason is just that it takes longer to run those types of simulations. So your simulation time step is governed by your shortest orbital period in your simulation. So if you want to include Mercury in your simulations, your smallest time step is going to be about 4 days. If you just want to include everything at Jupiter and beyond, you can increase your time step to about a half a year. But it was realized that there could be a problem with the terrestrial planets during a giant planet instability. So, normally when we think about planet orbits, you typically just think about the planet going around the sun or another star, and of course it just follows. It's the two-body problem, and it follows a fixed ellipse. As soon as you get another planet in there, though, you get non-Keplerian motion. And so the planet, due to planet-planet perturbations, this inner planet is not going to wind up in the exact same spot that it started in if you follow it for one revolution around the sun. And as a result, if you imagine the trajectories of these planets as ellipses, due to planet-planet interactions, what happens over time is those ellipses rotate. And so this is called precession. And the elliptical path that these two bodies take around the sun slowly precess over time. And they precess in our own solar system on periods of tens of thousands of years, roughly to hundreds of thousands of years, depending on where you are. And so that happens for every planet in our solar system. And this introduces the idea of the secular resonance. So if two planets happen to precess at the same rate, like this, where the orientation of their ellipses is always the same relative to one another, that's basically a secular resonance. And when you're in a secular resonance, this can dramatically increase your eccentricity or inclination. And so I have just shown right here Jupiter and Mercury. And so in this case, if you put Mercury in a secular resonance with Jupiter, its eccentricity increases dramatically. And if its eccentricity increases dramatically, it's probably going to hit either the Sun or Venus, and that would be bad for the stability of the inner solar system. So the reason this is a problem, well, I should say that this is not a problem today first. So basically each planet, if you look at the precession of its eccentricity vector, each planet effectively has a dominant frequency. And so those frequencies are listed in arc seconds per year here for all the planets at Jupiter and interior. And one thing to notice right away is that Jupiter precesses more slowly than all the inner planets. But another thing to notice is that these two values, the one for Mercury and the one for Jupiter, are not too far apart. So Mercury precesses at 5.6 arc seconds per year, and Jupiter's at 4.26. And the other thing to note here is that the terrestrial planets really don't affect the precession rate of Jupiter. So there's so much less massive. That's not ultimately what causes Jupiter to precess. What ultimately sets Jupiter's precession rate is the orientation of Saturn relative to Jupiter. And so where you stick Saturn basically sets the precession rate of Jupiter. And so you can run numerical experiments, and you can derive this analytically as well, where you can look at the Jovian precession frequency, Jupiter's precession frequency, as a function of Jupiter and Saturn's period ratio. And this was done. This has been done before, but this is from a paper by Ramon Brasser and others in 2009. And basically what they do is they vary the period ratio of Jupiter and Saturn as a function of, they vary it from the initial conditions of the Nice model. So the Nice model proposes that they start off near their 3:2 mean motion resonance, and it evolves all the way until you get to the modern value of 2.48. And so the point of this is that Jupiter's precession frequency varies greatly. And in particular, it really ramps up near the 2-to-1 resonance because of resonant perturbations on Jupiter's orbit. And so you see this precession frequency shoot up right here and then drop as you get on the other side of the 2-to-1 resonance. And the horizontal lines right here mark the precession rates of the terrestrial planets. And so the point of this is to go, if you want Jupiter and Saturn to go from a configuration, start at a configuration over here and wind up as a configuration over here, and you want to do this smoothly, you're going to pass through secular resonances with the terrestrial planets, which is probably bad for the stability of the inner solar system. And so to get around this, well, actually, sorry, I'm getting ahead of myself. And just to illustrate this a little bit more, here's one simulation where in the same paper, they started Jupiter and Saturn just beyond the 2-to-1 mean motion resonance. And then they smoothly migrated Saturn until the period ratio reached its modern value today. In the bottom panel, here is the evolution of the terrestrial planets as a result of this evolution of Jupiter and Saturn. And the one to pay attention here, they're not marked, but this upper one is Mercury. So we start off Mercury with an eccentricity of like 0.1. It bounces around. You can see that it's getting higher and higher, and they conveniently stop the simulation right here. But what will ultimately happen is once you reach basically what's happened here is Mercury's driven to a higher eccentricity than what we see today. And this is actually, it turns out, is a pretty mellow case. Oftentimes, Mercury is completely lost from the system, either due to hitting the Sun or Venus.
Sorry?
Yeah?
What are these really small variations at the top left?
Oh, yeah. You mean these small things right here? I don't know off the top of my head.
Just numerical, or is it?
Yeah, I think I don't know off the top of my head. I'm sorry. Yeah. So anyways, So that's a problem if you want to have the inner solar system remain stable during a giant planet instability. So to get around this, they invoked a new evolution for Jupiter and Saturn. So basically, instead of having this smooth evolution from 1.5 to 2.5, you have this, you start off smoothly evolving, and then you almost instantaneously jump from like 1.8 up to 2.3 and avoid that whole danger zone of secular resonances. And so, I mean, obviously, this is pretty contrived right here. How could you have a jump like this? Well, one way you can have this is rather than having Jupiter scattering a bunch of small planetesimals, you have Jupiter, because small planetesimals is ultimately what's driving the smooth part of this plot. Let's have Jupiter scatter a large planet-sized body, so a large like ice giant-sized body. And so in order to make that happen, you basically need to add an extra ice giant to the early solar system, because once Jupiter starts to scatter something, by far the most likely result is that object will be ejected completely. So that led to, yeah. This is the jumping Jupiter scenario, yeah. Where you basically save the inner solar system by having Jupiter and Saturn instantaneously jump in their period ratio, or almost instantaneously. And so this is an example of the jumping Jupiter scenario. So to make this work efficiently, you have to add an additional giant planet. And so basically you add in another Uranus-Neptune mass planet. And so that's shown, this is from a paper by David Nisvorny in 2011, where you have, what you can see here is what it looks like the previous plot. So you have after the instability, you have Jupiter, Saturn, Uranus, and Neptune evolving smoothly. But before then, before the instability occurs, you actually have a fifth giant planet in here, and it's quickly ejected out of the solar system completely. And if you look at the evolution of the period ratio of Jupiter and Saturn, basically you start off at 1.5, and all of a sudden Jupiter ejects the ice giant, and due to the energy required for that ejection, the period ratio of Jupiter and Saturn immediately jumps from about 1.6 up to about 2.3. And then you have another period of smooth migration after that. Yeah?
So if it jumps in that manner, two questions. First, how massive does that ice giant have to be to cause that much jumping?
Actually, it doesn't. It has to be about 15 Earth masses or so.
Okay, so that's not so much.
Yeah.
And then the second thing is, but now it looks like it's jumping over the 2-to-1 resonance, and I thought the whole point was to have the 2-to-1 resonance to cause instability.
Yeah. So basically, the original papers focused on the 2-to-1 resonance, and it's slightly more complicated than that. It turns out that if you start everything in a compact configuration, in a compact resonant configuration, once the resonances unlock from the initial erosion of the primordial Kuiper belt, it's almost guaranteed to go unstable regardless of the 2-to-1 mean motion resonance. So I kind of oversimplified things a bit there. But yeah, the original trigger for the instability was the 2-to-1 resonance, but if you have a 5-planet configuration and you break the resonance configuration, or the resonance, it'll lead to scattering pretty quickly. So basically, yeah, in this paper they explore this idea of an extra ice giant, and they find that pretty consistently you can jump over this gray zone, which is where you trigger these secular resonances between, or where you find these secular resonances between Jupiter and Mercury, and also Jupiter and Venus, actually. And they also looked at a few 6-planet configurations, 6 giant planet configurations. They found those worked as well, although at a lower probability. Yeah. Can you say that? I missed the first part of that.
Isn't the secular frequency is going to change quite a lot as they're changing the giant planets?
Yes. So the change in, so basically, I think the main, you're talking about the change in G1 and G2? Yeah. So I think G1 and G2 will change marginally, but not a huge amount. Because Jupiter's evolution, so it starts off, really what's happening is Saturn's moving quite a bit. So Jupiter's evolution starts off at about 5.5 and moves to 5.1, 5.2. So it's not a huge change. So they will change by a small amount. It's really the approach of Saturn to the 2-to-1 resonance which really dramatically changes Jupiter's precession rate. One other aspect, though. When you solve this, avoiding this zone with a scattering of an ice giant, you introduce a potentially other new problem, though. So when Jupiter or Saturn ejects one of these ice giants, it leads to a temporarily large increase in Jupiter's eccentricity. So one of the reasons the Earth and Venus and Mars and Jupiter undergo eccentricity fluctuations is because they're being forced, that eccentricity is being forced by the fact that Jupiter has an eccentricity. And so if you pump up Jupiter's eccentricity, you increase the amount of forcing on the terrestrial planets. So this might not actually save you. And so we wanted to investigate how well does the jumping Jupiter scenario actually preserve the stability, preserve the inner planets of the solar system. And so to do this, basically we repeated what other people did, is we used the Mercury simulation package to integrate many systems of 5 giant planets right up to the point of instability. We actually waited for them to lose a planet, then we rewound the system by one time step, or one time output. And then what you do is you go back and you embed the terrestrial planets into the system we want to give them the best chance of survival. So we put them on initially circular coplanar orbits. And then we integrate the system through the instability and integrate it to the modern epoch. We integrate it for another 4 billion years. And to actually assess the probability of success of this scenario, we ran hundreds of different simulations, hundreds of different initial conditions, and looked at how often the solar system was reproduced. And so this is just an example of what we did. So right here we have eccentricity versus semi-major axis of the outer solar system. So here's our initial conditions. We have Jupiter, Saturn, and 3 ice giants. And they're surrounded by a 20 Earth mass primordial Kuiper belt running from 18 AU out to 30 AU. And we run this simulation, and you can see that the giant planets are getting excited. And this is basically the point right before they go unstable. So then we add in, and in addition, I have marked here the period ratio of Saturn to Jupiter, and you can see it's right around 1.5 AU, or sorry, not AU, 1.5. So now we add in the terrestrial planets on circular coplanar orbits, so Mercury, Venus, Earth, and Mars. And so I'd like you to watch what happens to this period ratio. So even though we've ejected an ice giant just like we wanted to, the period ratio is still low. It's in that danger zone. It's at 2.2, 2.3, and it takes a long time to get above 2.3. And so you can see that the consequences of this are devastating for the inner planets. So we lost Mercury right away. We lost Venus, or it'll rerun right here. So we lose Mercury very quickly. Venus goes next. Earth gets very excited, which is bad for Mars. And so even though we added the extra ice giant and it was ejected by Jupiter, this didn't solve the problem. Not every Jupiter jump lands in the right space or in the right place. So this is just one example. So again, if the inner planets do survive, we continue to integrate for 4 billion years to ensure that they're stable. So here's an example of one where Jupiter and Saturn actually behave perfectly, though. So this is started right before the giant planets go unstable. We have our inner planets here on nicely ordered orbits. So we're going to let this go. And you can see that it immediately switched from 1.7 to 2.3. It did the jump perfectly, but you can also see that we're still missing Mercury here. So what happened here is that, well, let me go through that one more time. So Mercury survives initially, and then it gets pumped up to a high eccentricity. Oh, I'm sorry, this is the last one. Here's the one I wanted to show. So the jump occurs, Mercury survives for a little bit, but then it goes away. And so if we look in detail at what's going on, so here's the evolution of the giant planets right here. They're pericenters, apocenters, and semi-major axes. And so here's the ice giant that gets ejected. And so you can see that initially there is some excitation to the terrestrial planets, but then about 1 to 2 million years after the jump occurs, or after the giant planet instability occurs, there's a second period of excitation where Earth, Venus, and Mercury have their eccentricities driven even higher. And this is not due to secular perturbations from Jupiter. So you can see if you look at the period ratio of Jupiter to Saturn, like I said, the jump works perfectly. It starts at 1.75 and jumps to about 2.35. So it avoids that whole range where you'd expect secular resonances. what we think is going on is, because this is such a powerful jump, if you look at the eccentricities of Jupiter and Saturn, they get extremely high. In particular, the red here shows Saturn. So Saturn's eccentricity, which is right around 0.05 on average, jumps up to over 0.2 for a little bit before coming back down. Jupiter jumps up to, it approaches about 0.1, so about twice its current value. And so what happens is, if you look at the angular momentum deficit of the inner planets, so this is basically a measure of the degree that the inner planets' orbits deviate from perfectly circular, perfectly coplanar orbits. And so a value of 1 marks the angular momentum deficit of our modern solar system. So it starts off at 0, the jump occurs, and it goes up to 1 to 1.5. And then you see this second spike up right here, this huge spike to over 8. And that actually happens to coincide when Jupiter's eccentricity gets driven up to about 0.1. And so basically the forcing of Jupiter on the inner planet's orbits dramatically increases, and that destabilizes the solar system as well. So basically we found that the jumping Jupiter scenario is not always a perfect solution to the stability of the inner solar system. And so to evaluate all of our simulations, we developed a few different metrics, or a few different criteria for success. The first is that we wanted the simulation to be considered a success. We wanted the simulation to broadly reproduce the outer solar system. And basically what we wanted is we wanted 4 giant planets, and we wanted Jupiter and Saturn to end up with a period ratio beyond their 2-to-1 mean motion resonance. And to consider the inner solar system successfully reproduced, we wanted the system to finish with 4 stable terrestrial planets. So we didn't want to lose any terrestrial planets. And in addition to that, we wanted the terrestrial planets' eccentricities and inclinations to be comparable to their current values. So basically that angular momentum deficit that I mentioned in the last slide, we want the final value of that to be less than a factor of 2 of what we see in the modern solar system. And so when we ran 100 different simulations of each one of these initial conditions, so these different sets of simulations correspond to different resonant configurations of the giant planets and different masses of the primordial Kuiper belt. So we have 100 simulations for each one of these rows right here. And these are basically our success fractions here. So the outer solar system is reproduced basically in about 1 in 6 or so simulations. We end up with 4 giant planets, and Jupiter and Saturn are in the right position. If we require the outer solar system to be reproduced, and we require the inner solar system to retain all 4 planets, our success rate drops of order 0 to 2%. So it gets much lower. And if we then want those planets to actually be on orbits that resemble our current modern day orbits of the inner planets, then we basically have only 1 success case out of 300 simulations that we ran. And so those are not great odds. So what we conclude from this is that this supports the idea that instead of a delayed instability, you have an early instability. But it doesn't rule out. So it's hard. I talked about this a little bit yesterday, but this is not 0%. Our solar system, we know, looks different than a lot of other exoplanet systems. So it's not clear, when you start putting a lot of constraints on the solar system, it's going to be harder and harder to meet all those constraints. So it's not clear at one point you decide that this scenario is too improbable. But the bottom line is that if you want a late instability to reproduce our outer solar system, it relies on a relatively improbable sequence of events occurring. And so given that we can't quite rule it out, maybe we can look at other means to decide whether we have an early instability or a late instability. So the advantage of the early instability is that the terrestrial planets might not be formed yet. And so we wanted to see if there were any other ways we could constrain whether the instability is late or not. And so I mentioned before that initial simulations of the Nice model, to save time, they didn't model the dynamics of the inner solar system. Another numerical shortcut that these Nice model simulations usually take is the way the primordial disk around the giant planets is modeled. So typically what's done is these are modeled as semi-active particles. So what a semi-active particle does is it exerts a gravitational influence on the planets. And the planets exert gravitational influence on the disk particles, but the disk particles don't interact with each other. And so it's not clear how good of an approximation that is. It's not clear how much of the dynamics you're missing. And so to get at this, to see what the effects of a self-interacting disk would be, we've since run Nice model simulations using a new code called Genga that rather than running on an individual CPU, runs on GPUs. So the advantage of GPUs is you have a huge number of cores that can perform the same instructions on multiple threads in parallel. And so benchmarking of Genga versus the code Mercury we used shows that running on a modern GPU, it can outperform Mercury simulations by about a factor of 30. And so a factor of 30 is a big increase in computing efficiency, and it allows us to study the dynamics of a self-interacting disk consisting of about 1,000 bodies. And so this is one simulation right here showing the evolution of just the disk. So in this simulation, we've just started off a disk consisting of 1,000 bodies between 20 AU and 30 AU with no planets. So we'll evolve it over time. And you can see a couple different effects. Basically, the disk, due to particles scattering one another, they excite they self-excite all the eccentricities of the disk, and they also diffuse outward in semi-major axis. And so one of the ways you could tune the Nice model originally to give you a delayed instability was to have a gap between the disk and the planets, and that allowed the planets to stay stable longer. But if you run these simulations with a self-interacting disk, what you find is that it's very difficult to have a disk not start bleeding into the planets. And so this is a simulation with a self-interacting disk and 5 giant planets. And here's the time up here. And you can see in this particular simulation, after just 13 million years, we've lost the planet. And we wind up with a planetary configuration fairly similar to what we see today. And so we've run lots of these simulations. And basically what you're looking at here is you're looking at the time of instability versus the gap between the inner edge of the disk and the outermost giant planet. And so it runs from about 2 AU out to 6 AU. And so basically what we're finding is that, so these black points mark the points at which planetary instabilities occur. What we're finding is that no matter what you set the gap to, you can't have an instability that's delayed by more than a few tens of millions of years. Now you'll notice that there are black points up here as well. These are simulations where the giant planets have not gone unstable, but the tops of these air bars mark the point at which the disk has been, the planetesimal disk has been depleted by about a factor of 90% or so. And so in those cases, basically, we've retained all the planets, but they've just migrated through the disk. And so that really doesn't count as a success either. And if the planets were to go unstable, they'd wind up in a very different configuration than what we see today. And so the point of this is that there's this general trend with a larger gap. You get some increase in instability time, or instability delay. But the point of this is that even for our longest delays, we're only looking at about 30 million years versus about 500 million years. And so what we conclude from this is that if the giant planet's instability was delayed in our solar system, it's a very rare outcome. And our GPU simulations suggest that a massive primordial Kuiper belt can't remain stable for hundreds of millions of years. It can only remain stable in concert with the giant planets for about tens of millions of years. And so again, what we believe our work is telling us is that the Nice model instability actually occurred very early on, before the terrestrial planets were fully formed. And then you can get around preserving the stability of fully formed terrestrial planets. And so this means that the late heavy bombardment on the moon is either not real or had another origin. And another question that pops out from this work is how might the giant planet instability affect the process of terrestrial planet formation? Because it takes about roughly 100 million years to form our terrestrial planets. And so during this 100 million year window, we could have the giant planets go unstable, and how would that change things? So I'll just finish up with some ongoing work we have looking at terrestrial planet formation. So here's an example of a terrestrial planet formation simulation where we have a disk of rocky planetesimals that's started out on circular orbits between a half an AU to 4 AU. And then we have Jupiter, and then there's Saturn out here. So I'll run this simulation, and over time, these rocky planetesimals accrete more and more. This has been done, these types of simulations have been done many times in the past. And in general, these simulations, when we look at their final outcomes, they're evaluated with a few different metrics. They're evaluated in their ability to deliver water-rich asteroids to Earth, and their ability to produce the correct number of rocky planets, and their ability to produce relatively circular coplanar systems like our own. Recently, my grad student Matt Clement and I looked at their ability to reproduce the chaotic state, the long-term chaotic state of our own solar system. And then finally, another metric that these systems are evaluated on, or these simulations are evaluated on, are their ability to reproduce the correct masses. And so that's what I want to focus on here. So you can see that this simulation, this particular simulation right here, formed a 1 Earth mass planet at 1 AU, formed something that looks like Venus at about 0.7 AU, and it formed a Mars analog that's about 10 times the mass of Mars. So it turns out that this is a very common outcome. If you tune your simulations to produce an Earth analog at 1 AU, you often end up getting an Earth mass planet at 1.5 AU. And so this was pointed out by Sean Raymond et al. In 2009, and he tried lots of different configurations of the giant planets to reproduce, to basically decrease the mass of Mars. And the most successful arrangement of giant planets was a simulation set that he called EEJS, where the eccentricities of Jupiter and Saturn were increased to twice their modern values. And so you can see when you increase the eccentricities of Jupiter and Saturn to twice their modern values, you strongly deplete the massive planets that you form beyond 1 AU. And so here's the masses of the real solar system marked in squares right here, and the small dots are masses from the actual simulations. And so this is a pretty good match right here. But then the question is, how do you get the giant planets' eccentricities back down to today? So I'm running a little short on time, so I'm going to skip this right here and just show you what I want to finish up with. So when that paper was written in 2009, we weren't really thinking about the idea of a giant planet system going unstable while the terrestrial planets were still forming. And in this plot that I showed you before, showing the evolution of the giant planets during an instability, what you see is that after the instability occurs, temporarily, Jupiter and Saturn's eccentricities get much higher than what they are today, and then dynamical friction damps them back down as they eject more and more of that primordial disk. And so what we want to do is we want to, again, evolve the giant planets until an instability, and then embed a rocky planetesimal disk and look at what happens, how the giant planet instability affects terrestrial planet formation. So that's work that's ongoing right now with my grad student, Matt Clement. And so here's the inner solar system. You have a rocky disk of planetesimals. Here's the outer solar system. It's about to go unstable. And just for kicks, here's the Kuiper belt that we end up forming at the end. And these lines mark the actual positions of the real planets today. And so we're going to leave this evolve. And what you see here is basically this simulation, even though it matches the outer solar system pretty much exactly, the inner solar system winds up with the same problem that we always have. So Mars is a very massive planet in the simulation, and it's not in the real solar system. But this is just one particular simulation. So we're still running simulations like at the moment. And so we also have other simulations like this one shown here where the results are much more encouraging. So in this case, we actually lose Uranus and Neptune in this case, but Jupiter and Saturn still wind up in their modern locations. And if you look at the inner solar system, what you see is that we wind up with something at the end that looks very similar to the real solar system. These movies go a little slow, but you can see basically we don't quite get down to a Mars mass, but we get a Mars analog that's significantly less massive than our Earth analog. And so these are still in the process of running, and I'll just cut to the chase here, right here at the end. So what we can conclude from this is that a delayed giant instability is very difficult to reconcile with the survival of the terrestrial planets, and then it's also very difficult to reconcile with the self-stirring of the primordial Kuiper belt. If you put a primordial Kuiper belt that's tens of Earth masses just beyond the giant planets, what happens is the interactions between Kuiper belt objects basically causes the disk to diffuse, and you end up triggering an instability very early. And so what we've seen is that from our ongoing work is that an early instability will almost certainly alter the process of terrestrial planet formation and likely deplete terrestrial material beyond the Earth's orbit, possibly helping solve this small Mars mass problem that exists in terrestrial planet formation models. So with that, I'll take any questions you have. Thanks.
Do you get a grant pack?
What about Grand Tech?
Do you get a grant pack and then
No. So to get the Grand Tech, you need a gas disk. And so we don't include a gas disk. Yeah.
Sorry, so if Planet 9 ended up being confirmed, for example, does this mean that jumping Jupiter definitely happened?
No. I don't think it means that the jumping Jupiter necessarily happened. But it seems like if there's an instability, it's not very far-fetched at all that you would lose at least one planet. And it turns out that the eccentricity increase that you get from the jumping Jupiter scenario can help you solve the small Mars mass problem. It appears from our, that's yet to be submitted, but the results look promising. Yeah.
Do you have any ideas how much the self-stirring is dependent on how it made it possible to see this?
No, so that's something so we have to run some convergence tests. So we can't really run any more simulations with more particles, but we're going to run batches with less particles to see the trend there. But that is a concern for sure. But I mean, yes, it's a concern, and we'll never model with the real number of particles. But our particle mass right now is about 5 Pluto masses, and really it would be nice to get down to about a Pluto mass because it's thought that the real disk had roughly 1,000 to 2,000 Pluto mass bodies based on work that David Nisworny's done. Yeah.
It's possible to do every situation, but for your survival of the inner planets in a jumping Jupiter model, if you're starting with 4 inner planets, why not start with 5 or 6 and try to see if you get a surviving population somewhat similar?
Yeah, I mean, so that's another idea that's crossed our head. So really the only constraint on terrestrial planet formation, the time scale, is that we've had the moon forming impact at roughly 100 million years in. And so who knows what the terrestrial planets looked like before then. I mean, it's possible that that protoplanet that slammed into the Earth could have been a part of a stable configuration that was disrupted through a process like this. And yeah, I agree. Starting with 5 or 6 planets and looking at what happened, that's another reasonable way to maybe solve this problem with the late instability. But yeah, I mean the amount of parameter space blows up. I mean, as you add more and more knobs. Exactly, that's true. You're right. Yeah. Yeah, you're right. Yeah. Yeah.
Sorry, so with Jinka, do you get binary comments?
Binary. So that's something that I'm interested in. You mean in the Kuiper belt?
Yeah.
Yeah. So I don't know if. So yeah, one issue is that there's these Kuiper belt objects that are very weakly bound. They're in binaries, ultra-wide binaries, and so can they survive this violent evolution? That's something we haven't looked at all yet. I know Alex Parker looked at that a few years ago and found that.
Because it's a very active issue right now. If 67B was 2 comments were joined or 1 comment.
Oh, I see what you're saying.
So
yeah.
It's quite an issue right now.
Yeah. Yeah, we haven't thought about binary Kuiper belt objects at all.
Why do they have to survive? Why can't they form binaries, especially if they're weakly bound, just dynamical interactions at any time? There should be some population of these things that we call bound at all times, right?
Yes. So you're asking like the very weakly bound ones?
Why did the wide binaries have to survive some kind of stirring? I'm asking, is there not just a population of wide binaries in an equilibrium system?
Yeah, so the wide binaries are kind of a transient tail, is what you're saying, of a tight. Yeah, so I actually happen to believe that. But there have been a lot of papers written about how the existence of those ultra-wide binaries serve as a constraint on the level of violence that happened early on in the outer solar system evolution. So, yeah, I'm on the same page. Yeah, I don't think they're as strong of a constraint as they've been painted to be. Yeah.
Has there been any hope of maybe
so you're running these simulations of just a pentacle that's stirred up, and I know that there's some papers like Rapikov who try to analytically kind of track that, and have you maybe tried to compare that, or basically is there a way to add an ingredient where you have semi-active particles, but you add some self-stirred?
Yeah, that's a possibility for sure. And I mean, something else I've thought about is that that Ganga code has semi-active particle mode in it too. So we could lay down like 1,000 real particles and then put, kind of like what's done with terrestrial planet formation simulations, where you have these fully interacting embryos, and then on top of that you have a much more populous planetesimal or semi-active population. So yeah, and I think a way to do that is, you could look at some of those analytical prescriptions and see how well they're produced for this very granular simulation I showed here, and then that would give you an idea about whether it's reasonable to just scale it up for larger numbers. Yeah.
Okay, thank you.
Okay, thanks.